In the linked video, we have learned about 3 different types of fits in more detail. Let us briefly review the most important points again here. A fit generally refers to the joining condition of 2 components, for example a shaft fitted into a hole. Depending on the position of the tolerance zones of the hole and the shaft, different types of fits result. If the tolerance zone of the shaft lies entirely below the tolerance zone of the hole, the shaft is always smaller than the hole, and this is called a clearance fit. If the tolerance zone of the shaft lies entirely above the tolerance zone of the hole, the shaft is always larger than the hole, and this is called an interference fit or a press fit. If the tolerance zones of the shaft and the hole overlap, a small clearance or a small interference may exist, and this is called a transition fit. For fits, the tolerance zones are described by ISO tolerance grades. In the linked video, we have already explained the basics of tolerances in detail. Let us briefly repeat the most important points here as well. ISO tolerance grades consist of a letter and a number. The number, called the IT fundamental tolerance grade, defines the size of the tolerance zone. The letter, called the fundamental deviation, describes the position of the tolerance zone relative to the datum line of the nominal size. The fundamental deviations, and thus the position of the tolerance zones, differ depending on whether it is a shaft or a hole. For shafts, the fundamental deviations are indicated by lowercase letters, and for holes by uppercase letters. In the following, we will take a closer look at the system behind the fundamental deviations. Let us first examine the positions of the tolerance zones of holes in more detail. We have already become familiar with the tolerance zone H in the video on the basics of tolerances and in the video on fits. This is a special position because the tolerance zone starts exactly at the datum line and the lower limit size therefore corresponds exactly to the nominal size. In addition, there are many other fundamental deviations which are arranged alphabetically. It starts with the fundamental deviation A, which has the largest positive deviations. In alphabetical order, the deviations then become smaller. Up to and including the fundamental deviation H, the tolerance zones always lie in the positive range, and both limit deviations are therefore positive. The tolerance zones with the fundamental deviations J and K vary around the datum line and therefore have a positive upper deviation and a negative lower deviation. From the fundamental deviation with the letter M, the tolerance zones lie entirely in the negative range, and both limit deviations are thus negative. It is noticeable that not all letters of the alphabet are used for the designation of the fundamental deviations. These are, for example, the letters I, L, O, Q, and W. This is purely for practical reasons, as these letters often cause confusion. For example, the letter O can easily be confused with a 0 or, if the drawing is dirty, with a Q. The same applies to the letter I, which could easily be confused with a J. For this reason, the mentioned letters are omitted. It should be noted that in addition to the listed fundamental deviations, there are further fundamental deviations which are however rarely used in practice. For example, there are the fundamental deviations with the letter combinations ZA, ZB, and ZC, which are used for very large press fits and follow the fundamental deviation Z. In addition, there is a special fundamental deviation which is similar in position to the fundamental deviation J, but exactly symmetrical to the datum line, and is therefore designated with the letter combination JS. For precision mechanics, there are also some special tolerance zones with the letter combinations CD, EF, and FG, which are however only defined up to a nominal size of 10 mm. For now, we will focus on the specified fundamental deviations. It is important to note that these letters actually represent specific numerical values. The fundamental deviation is generally defined as the deviation closest to the datum line. For the tolerance zones A to H of holes, the fundamental deviation corresponds to the lower deviation. For the tolerance zones K to Z, the upper deviation is the fundamental deviation. The nominal size J is a special case, and depending on the nominal size can have either the upper or the lower deviation as the fundamental deviation. Let us now schematically examine the tolerance zones for shafts. These are basically structured the same way as for holes. Compared to the positions of the tolerance zones of holes, the tolerance zones of shafts can essentially be imagined as mirrored at the datum line. To indicate a shaft, the fundamental deviations are denoted by lowercase letters. With the exception of the tolerance zones starting from the letter J, which for shafts can lie slightly higher depending on the tolerance grade than the mirror image suggests, the fundamental deviations of holes and shafts are generally relatively symmetrical to the datum line. Therefore, the statement about the fundamental deviation as the deviation closest to the datum line also applies to the tolerance zones of shafts. In this case, for the tolerance zones A to H, The upper deviation corresponds to the fundamental deviation. For the tolerance zones K to Z, the lower deviation again represents the fundamental deviation. In this sense, the fundamental deviations of the tolerance zones of holes and shafts are essentially mirrored at the datum line. For example, a shaft with a nominal size of 20 mm and the tolerance zone C has an upper deviation defined as the fundamental deviation of -110 micrometers. A hole with the same nominal size of 20 mm and the corresponding tolerance zone C then has a lower deviation defined as the fundamental deviation of +110 micrometers. Or the tolerance zone S has, for example, a fundamental deviation of -35 micrometers for a hole with a nominal size of 20 mm and tolerance grade IT8, while the corresponding tolerance zone S for the shaft then has a fundamental deviation of +35 micrometers. Fundamental deviations are basically defined relatively symmetrically within certain nominal size ranges for both shafts and holes. With increasing fundamental tolerance grades, for example from IT4 through IT6 up to IT8, essentially only the size of the tolerance zones changes, not the fundamental position of the deviations, even though there are adjustments especially for holes depending on the tolerance grade. This is the only way to ensure later in the fit systems that fundamental deviation combinations of holes and shafts always lead to the same type of fit regardless of the fundamental tolerance grade, for example to a clearance fit, a transition fit, or an interference fit. To understand the purpose of the fit systems explained later, we first take a closer look at the manufacturing and verification of dimensional accuracy for a fit in holes. Let us consider as an example the production of a hole with a nominal size of 20 mm and tolerance grade H7. In this case, the lower limit deviation is 0 and the upper limit deviation is 21 micrometers. Drilling with a twist drill is usually not sufficient here to meet the required dimensional tolerance of 21 micrometers. This generally applies to fundamental tolerance grades up to 10, which cannot be achieved with conventional twist drills. Therefore, the hole is initially pre-drilled with a twist drill so that the hole is approximately 0.2 mm smaller than the nominal size. Then the hole is reamed to the desired size with a special tool called a reamer. In the linked video you will find more information about drilling and reaming. Reamers are much more precise than twist drills and are specially designed for a specific nominal size and tolerance grade, in our case for the nominal size 20 mm with tolerance grade H7. Nevertheless, it must be checked afterwards whether the required dimensional tolerance has actually been met. Because the reamer, like any tool, is subject to wear and this can cause dimensional deviations. An unsteady run of the drilling machine or incorrect clamping of the reamer as well as the use of an unsuitable cutting fluid or insufficient cutting fluid pressure can compromise the dimensional accuracy. To verify compliance with the tolerance of 21 micrometers, a simple caliper is not sufficient. The accuracy of digital calipers is only in the range of about 20 micrometers. So if the caliper shows a measurement of 20.01 millimeters, the actual size could also be 20.03 or 19.99 millimeters. In both cases, we would already be outside the tolerance range, which lies between exactly 20 and 20.021 millimeters. Therefore, special measuring tools in the form of so-called limit gauges are required to check the dimensional accuracy of fits. In the case of gauging holes, this is called a limit gauge plug. Like reamers, limit gauge plugs are specially designed for a nominal size and a tolerance grade, in our case for the fit 20H7. Limit gauge plugs have two checking sides. A so-called go side, whose diameter is manufactured very precisely at the minimum size of 20.000 millimeters, and a no-go side, which is manufactured at the maximum size of 20.021 millimeters. The no-go side is usually marked with a red plastic ring or a red marking. The go side is used to check whether the bore is below the minimum dimension. For this purpose, the limit plug gauge with the go side is placed onto the bore. Since the bore must in any case be larger than the go side manufactured to the minimum dimension of 20 millimeters, for example 20.006 millimeters, the limit plug gauge must fit into the bore with this side without significant pressure. This ensures that our bore does not fall below the minimum dimension of exactly 20 millimeters in this case. If the actual dimension of the bore were for example 19.994 millimeters, the minimum dimension of 20 millimeters would be undershot and the limit plug gauge would not fit into the bore with the go side. Therefore, the limit plug gauge must always slide into the bore with the go side without great force in order to check dimensional accuracy. After the minimum dimension has been checked with the go side, the no-go side is used to verify whether the bore exceeds the maximum dimension. Since the bore must in every case be smaller than the no-go side manufactured to the maximum dimension of 20.021 mm, the limit plug gauge with this side must not fit into the bore. This ensures that our bore does not exceed the maximum dimension of 20.021 mm in this case. If the actual dimension of the bore were, for example, 20.027 mm, the maximum dimension of 20.021 mm would be exceeded and the limit plug gauge would fit into the bore with the no-go side. Therefore, the limit plug gauge must not fit into the bore with a no-go side to verify dimensional accuracy. So note, the limit plug gauge must slide into the bore with the go side using little force, while the no-go side must not fit into the bore. If this is fulfilled, the bore is within the required tolerance. A brief note regarding the terms go and no-go side. The no-go side is named so because if it fits into the bore, the part is immediately scrap, meaning it can no longer be repaired. In this case, the bore is too large and cannot be reduced afterwards. However, if the limit plug gauge does not slide into the bore with the go side as intended, the bore is not technically good, but it is not immediately scrap either, it is simply too small. In this case, there is the possibility to rework the bore with a reamer to enlarge it slightly. In contrast to the manufacturing of fits for bores, which require special tools in the form of reamers, fits for shafts can generally be produced using conventional lathes and turning tools. As an example, consider manufacturing a shaft step with a diameter 20F7. For measuring shaft diameters, there are precise measuring instruments such as a micrometer screw gauge. Digital micrometer screw gauges achieve accuracies that are approximately 10 times better than conventional calipers. Thus, accuracies in the range of 2 micrometers can be achieved. This is often sufficient for the inspection of shaft fits. However, in mass production, the use of a micrometer screw gauge for cost-effective inspection of dimensional accuracy is not particularly suitable due to the time required. Therefore, similar to gauges for bores, there are also special limit gauges for shafts for quick verification of dimensional accuracy. These are called limit snap gauges. Limit snap gauges operate according to the same principle as limit plug gauges. They also have a go side and a no-go side. The no-go side is again marked with red color. In this case, however, the no-go side is manufactured to the minimum dimension and the go side to the maximum dimension, exactly the opposite of limit plug gauges. The no-go side is used to check whether the shaft is below the minimum dimension. For this purpose, an attempt is made to move the shaft through the no-go side without significant force. If this were possible, the shaft would obviously be smaller than the minimum dimension. In this case, the shaft could no longer be reworked and would therefore be scrap. The shaft must not pass through the no-go side, because only then is the shaft larger than the minimum dimension. Subsequently, the go side is used to check whether the shaft does not exceed the maximum dimension. The shaft must pass through the go side without great force. Only then does the shaft not exceed the maximum dimension. If the shaft were larger than the maximum dimension, it would not fit through the go side. In this case, the shaft can still be reworked to correct the dimension. So note, the shaft must be able to slide through the go side of the limit snap gauge with little force, while it must not fit through the no-go side. If this is fulfilled, the shaft is within the required tolerance. Let us return once again to the different fundamental deviations of fits for holes and shafts. If all possible combinations of the fundamental deviations between hole and shaft were allowed, countless variations would result. In particular, manufacturing bores with expensive reamers and subsequently checking dimensional accuracy with equally expensive limit plug gauges would lead to an enormous number of different reamers and limit plug gauges. As an example, consider a nominal size of 20 millimeters. For this nominal size, we need not only one reamer and one limit plug gauge each for the 21 listed fundamental deviations from A to Z, but within one fundamental deviation we must in any case cover at least the 6 common tolerance grades between IT5 and IT10. Thus, we require 21 times 6 reamers and limit plug gauges, a total of 252 tools. This would mean tool costs of several tens of thousands of euros. And this would cover only one nominal size of 20 millimeters. Therefore, especially for holes, it is sensible not to allow all fundamental deviations, but to consistently select one fundamental deviation and preferably use it. For holes, this preferably uniformly used fundamental deviation is the fundamental deviation with the letter H. This is then referred to as the hole basis system. Remember, when applying the hole basis system, the holes uniformly receive the fundamental deviation H. The lower deviation is in this case always 0, so that the minimum dimension of the bore always corresponds to the nominal size. Depending on whether a clearance fit, an interference fit, or a transition fit is to be produced with a mating shaft, the fundamental deviation of the shaft is chosen accordingly. We see that in the whole basis system the fundamental deviations of the shaft between A and H lie completely below the tolerance zone H of the bore. In the whole basis system, therefore, the fundamental deviations of the shaft in the range between A and H lead to a clearance fit. The tolerance zones P to Z of the shaft, on the other hand, lie entirely above the tolerance zone H of the bore. In the whole basis system, the fundamental deviations of the shaft in this range therefore lead to an interference fit. In contrast, the fundamental deviation H of the bore overlaps with the tolerance zones of the shaft in the range between J and N. These fundamental deviations of the shaft thus characterize the range of transition fits. We will see later that the German standard DIN 7157 further restricts the possible combinations of tolerance grades. In addition to the whole basis system, there is also a shaft basis system. Analogous to the whole basis system, the uniform fundamental deviation H is specified for the shaft in this case. Note that in both the whole and the fit basis system, the tolerance zones H always start at the nominal size and then extend into the material of the whole or the material of the shaft, so to speak. Analogous to the whole basis system, in the shaft basis system, depending on whether a clearance fit, interference fit, or transition fit is to be produced with a mating hole, the fundamental deviation of the hole is chosen accordingly. We see that in the shaft basis system, the fundamental deviations of the hole between A and H lie completely above the tolerance zone H of the shaft. In the shaft basis system, therefore, the fundamental deviations in the range between A and H also lead to a clearance fit. The tolerance zones P to Z of the hole, on the other hand, lie entirely below the tolerance zone H of the shaft. In the shaft basis system, these again lead to an interference fit. A transition fit with overlapping tolerance zones also results in the range between J and N. Here as well, however, the German standard DIN 7157 further restricts the possible combinations of tolerance grades. The German standard DIN 7157 specifies a total of 14 combinations for the whole basis system, which, as shown, range from the green-marked clearance fits through the yellow-colored transition fits to the red-highlighted interference fits. For the shaft basis system, the standard defines 11 tolerance grade combinations in the range of clearance fits. 4 transition fits and interference fits. No combinations are prescribed in this fit system. Therefore, transition and interference fits are primarily produced in the whole basis system. Of the tolerance grade combinations shown, the red-marked ones from the so-called Series 1 are preferred. If this series is not sufficient, then the blue-marked Series 2 is to be used as an alternative. There is a special feature for the tolerance grades H7X8 and H7U8. Up to a nominal size of 24 mm inclusive, the tolerance grade combination H7X8 should be used, and for nominal sizes larger than 24 mm, the combination H7U8. For most cases encountered in practice, the tolerance grade combinations of Series 1 and Series 2 shown are sufficient. Deviations from these combinations should only occur in exceptional cases. This is, for example, the case when selecting fits for rolling bearings. When considering the tolerance grade combinations, it is noticeable that the shaft usually has a lower fundamental tolerance grade than the whole. This is due to the already mentioned reason that reamers and the corresponding limit plug gauges are very expensive, especially when it comes to very fine fundamental tolerance grades. In practice, it is therefore often more economical to produce finer tolerances on the lathe, which does not require expensive tools. In principle, the tolerance grades of hole and shaft should not differ by more than 2 fundamental tolerance grades. Usually, the fundamental tolerance grade of the shaft is equal to or only 1 grade lower than that of the hole. A difference of 3 or more fundamental tolerance grades is not practical. After all, a fit is only as accurate as the largest fundamental tolerance grade. If the hole already has a relatively coarse tolerance, the fit does not become more accurate by making the shaft tolerance grade smaller. Only the manufacturing effort for the shaft, and thus the costs, increase disproportionately. For example, the fit 20H7F7 has a minimum clearance of 20 micrometers and a maximum clearance of 62 micrometers. If one wanted to produce the shaft 2 tolerance grades finer with F5, this would only be possible by ultra-precision turning and thus with very high manufacturing costs. However, the fit would still have a minimum clearance of 20 micrometers, so the minimum clearance would not change. The maximum clearance would only decrease from 62 to 50 micrometers. The marginal reduction of the maximum clearance by the very fine tolerance grade with unchanged minimum clearance is therefore disproportionate to the enormous manufacturing effort.